problem solving session for traffic engineering. So this is week number 8 of our sessions. And I am Sedu Vinayagan, a PhD scholar in the Civil Engineering Department at IIT Madras. So as usual, we'll start with an overview of the concepts that were taught in this week, and then we'll go into the problems. So this week, we were looking at actuated signals, right? So last week we were looking at pre-time signal analysis. So this is the other type of signals, which is the actuated signals. So we had 5 lectures. The first one was an introduction to actuated signals, right? So what are the features that are available in the actuated signals, okay, the controllers, and then how to design actuated signals, and then operational analysis of actuated signals, okay. So when it comes to actuated signals, so we have two major types. So one is a fully actuated signal, and the second is a semi-actuated signal. So what is the difference between these two is in a fully actuated signal, all the approaches at the intersection or to the intersection will be actuated. Okay, so there will be detectors on all the different approaches to the signal, and then based on the demand data that is collected from these different detectors, the cycle length and the green time and the phase sequence allocations will be adjusted. So that is the fully actuated signal. So whereas the semi-actuated signal, only the minor approach will be actuated. Okay, so this is more applicable when a major road crosses a minor road. Right, in this case, as you can imagine, the major road will be having the very high demand, or the most demand will be carried by the major road, and the minor road will have only lesser demand, okay, relatively lesser demand, and that will also be spread out throughout the day, right? So therefore the major road is what gets the priority. So therefore see, the actuated phase will be corresponding to the minor road, right? So there won't be any actuation on the major road, and the actuated phase will only correspond to the minor roads, right? So whenever there is demand on the minor road, only then the phase sequence or the cycle settings have to change, right? So otherwise only a minimum green is enough for the minor movement. So those are the two major types within the actuated signals. And so when it comes to the features for the actuated controllers, so the major thing is we have to detect the traffic, right? So for that we have two types of detection. So the first type is a point detection, point, or this is also called as passage detection, right? So here, so we have a roadway, right? So the approach to the intersection, and then the detection will happen only at a point along that approach, right? So when a vehicle crosses our detector, the passage detector, so we will know that a vehicle has passed, right? So this will raise an electric pulse, right? So whenever a vehicle crosses, an electric pulse will be generated. So that tells the controller that at least one vehicle has is present in that particular approach, right? So therefore service is required for this approach, right? So that's what the point detection will tell us. The second one is called as area detection. Okay, so area is also called as presence detection, right? So this is the natural extension of the passage detection. So here we have, the detector will cover a certain length of the approach, right? Instead of a single point, a certain length of the approach will be covered. So whenever a vehicle enters right? And as long as some part of the vehicle still remains within the detector area, right? So continuous. So this is, let us say, discrete electric pulse. So here you'll get continuous electric pulses will be generated as long as the vehicle is within the our detection area, right? So this is the second type of detection that we can do. And in this in the passage detection, we do not count the number of vehicles that are crossing, right? So even if multiple vehicles are crossing our passage point, so we will only consider it, we will not keep a count of number of vehicles crossing. We will only consider that at least one vehicle is present in the approach, whereas in the area detection we can also determine the number of vehicles that are stored in our detector area. So that is possible in the area detection, right? So so that's what we looked at in the controller features, and then we looked at how to design the actuated signals, right? So when it comes to design of actuated signals, we have to decide on, right, cycle lengths, right? Interval lengths like green times, yellow time, right? So all this things, and also the phase sequence, these need to be detected, right? So we looked at how we will calculate these green times, right? So first, for the green time, in case of, it depends on, again, how you calculate this will depend on the controller type that we are using, or the detector type that we are using, right? So if we are using a passage detection, so what we will assume is, say the stop line for that intersection is here, and if we have detected a vehicle has crossed the passage point, we'll assume that this whole length t, right, so between the stop line and the detector, is occupied by vehicles, right? So that is the assumption that we make when we are using a point detector, right? So and then based on the the minimum spacing that that between the vehicles, right? So we can find out the number of vehicles that need to be served, right? So this will not change from one cycle to the other, right? So if whenever one vehicle is crossed, it will always be whatever is the number of vehicles that can occupy this D length. So corresponding to that, we will give the green time. So that is the minimum green that we have to give. Whereas in a the continuous detection or the presence detection, so it should not be too far away from the stop line. So in that case, the number of vehicles that are within your area, that can be determined again based on the spacing, right? So with that, again, we can give the green time for those number of vehicles in the case of presence detector, right? So that's what we looked at, and then that is the minimum green time, and then we also can determine the critical cycle length. So what will be the critical cycle length? So critical cycle length is the cycle length where now you'll have the peak demand, right? So corresponding to the peak demand, so we have to determine. So when there is peak demand, so there is also a maximum green time that we have, that we can provide, right? So there is a minimum limit that we have decided. Similarly, there is a maximum limit. So whenever there is peak demand, so when we want to find what is the critical cycle length, so we'll assume that the maximum green time is achieved or is provided to the major road. Okay, let's say it is for phase A, and for the other side, the minor approach will provide the the minimum green, and then we calculate the the yellow plus all red interval. Okay, so the amber change interval plus the all red interval. So that determination of these two is same as what we did for the pre-time signal, right? So those are added to get the critical cycle length. Right, so that's how we design the actuated signals. And then we also looked at the operational analysis of actuated signal. So we looked at the steps, right? So we did not get into the detailed methodology, but we looked at an overview of what are the steps. So this is again mostly similar steps as what we did for the pre-time signals, except for some additional steps that we have, right? Like we have to, here the phase timings are not going to be the same, right? As in the pre-time signal, we have a constant cycle length, phase durations and interval durations, but here it has to be modified based on the the demand that is being detected, right? So therefore some changes will be there, but most of the steps will still remain the same. Then we looked at signal coordination. It's what is signal coordination? So it's basically, when you have a series of signals along a corridor, right? So when you have a series of signals that are present along a corridor close to each other, right? So signal coordination is basically when a vehicle that is, leaving an upstream signal, let us say signal 1, and then when it reaches the downstream signal, say signal number 2, if it can pass through these downstream series of signals without having to stop, right, or slow down, then we say that there is signal coordination, right? So what does this allow? This allows vehicles to pass through a series of signals that are closely located, so without having to slow down or stop, right? So how do we do that? So that's so first we have to determine whether we need the signal coordination or not, right? So here we looked at different criteria by which we decide whether the signal coordination is needed or not. So here we looked at the grouping of intersections, right? So grouping of intersection is basically determined based on the link length. So what is link length? So link length is nothing but the distance between the two successive signals, right? So our intersections, the roadway between the two successive sections, intersections is called as the link, right? So if the length of the link is less than half a mile, less than or equal to half a mile, right? So if they are closely packed, so in that case, it becomes advantageous if we provide this, if we coordinate those signals, right? So that's how we determine. So that is one way. The other way, so we have different indices which tells us whether the signal coordination have to be provided or not. So in that we looked at three different indices. One is interconnection, interconnection desirability index. Then we have the coupling index and a variant of the coupling index. Right, so these are different methods, right? So different values which can be calculated based on the distance between the signals and also the volume of traffic for different movements. And then once we get the value for these indices, so there are tables which tell you for different ranges of these indices whether we can consider the coordination or it is not required, or providing it is desirable or not, right? So those are also ways in which we can come up use to assess whether the signal coordination is needed. Okay, then we looked at the different types of signal coordination, right? So again there are two types. So one is traditional, another one is advanced. Okay, so these are types of signal coordination. So in traditional coordination, what happens? So again we have to predetermine what will be the set of the cycle length, the splits and offsets for different timing plans, right? So we'll have different plans for different conditions, and but we'll have a consistent cycle length and the splits and the offsets, right? So we'll look at what these are. But these have to be determined, manually. We have to tell it manually, right? So we have to identify that. Whereas in an advanced coordination system, so we don't have to manually specify this, So based on the measurements from the field, so all the cycle length, splits, and offsets, so these different parameters will be, determined without any explicit, specification, right? So those are the two methods or types. And then we looked at how to coordinate the planning system using a space-time diagram. Okay, so what is a space-time diagram? So space-time diagram is basically a 2D, a graph. So where your y-axis will be the space, that is nothing but your longitudinal roadway. Okay, longitudinal roadway direction, and your x-axis will be the time axis. Okay, so when you have a signal, right, so it can have certain red, green cycles, right? So basically you will plot the vehicle trajectories, right? As the vehicles pass through these roadway, so you can draw their trajectories, right? So what does the slope of these trajectories give us? The slope of these trajectories will give us the speed at which these vehicles are traveling, right? So by looking at the space-time diagram, so you get a visually, you can get a feel for what is happening in the system, right? So and that can be used to assess and then come up with different strategies or even evaluate whatever strategies have been developed, right? So that's how this space-time diagram will help us in the signal coordination. So here we'll again look at different concepts. So one is the vehicle trajectory, which can be plotted in this space-time diagram. So other one is the bandwidth, right? So what is a bandwidth? So bandwidth is basically, so when you have signal coordination, right? So the first vehicle, so let us say there is another signal where it had red and then it had green and then red. Okay. So bandwidth is nothing but this is the bandwidth. So the first and the last trajectories, right? So it's a pair of trajectories, right? So the first and the last pair of trajectories that can pass through your in the corridor without having to stop, right? So basically the vehicles which are experiencing this progression through the different intersections without having to stop, right? So we take the boundaries of those vehicle trajectories, right? So this is the first one to pass through, right? And this is the last vehicle to pass through without having to stop, right, at the two intersections. So the time gap between these two trajectories, so that will give you the bandwidth, right? So that's what we define as the bandwidth. And with respect to this, we have looked at what is the bandwidth efficiency. So bandwidth efficiency is nothing but the ratio of the bandwidth to the cycle length, right, multiplied by 100. So it is expressed as a percentage, right? So how much the total cycle length is being used for the progression of the vehicles. So that's what is the bandwidth efficiency. And with bandwidth efficiency, we also have the bandwidth capacity. Okay, so the capacity of a given bandwidth. So that is nothing but, so you have the saturation headway. So 3600 saturation flow 3600 by h into the number of lanes. Okay, this multiplied by your bandwidth efficiency. So that will give you the capacity of your bandwidth. Okay. So that's what we looked at in the second lecture. Then in the third lecture, we were looking at the different parameters for signal coordination. So what are the different parameters that are there? So one is we have to determine what are the different phases that needs coordination phases. Okay, so that is to be determined, right? So which phases will be actuated, which phases are not, right? So that is one of the parameters that we have to determine. Second is we have to calculate the cycle length. So this is another parameter. Then we have to determine the split, right? So how this whole cycle length will be split across the different phases, right? So all the phases have to be covered, right? So how are we going to make those split? And then there is this concept of force off. So what is force off? So force off is basically it's a point in time, right? So when even if there is a demand on a particular approach, the signal setting, the green will not be extended, right? So the signal will change and the other phase will be provided movement, right? So that's the force off. So again there is a decision that we have to make whether force off has to be employed or not, right? And if there is a force off employed, so what is the time limit that we have to give? And then there is offset. So what is an offset? So offset is basically, so when you have two different signal coordination, signals that are coordinated. So what we are looking at here is, say this is the first signal and this is the second signal. So the time at which first signal turned green, so let us say that is t1. So and the time at which the second signal turned green, so let us call that as t2, right? So obviously this t1 and t2, they need not be the same always, right? So there is some time gap between t1 and t2, right? And this gap t2 minus t1, right? So the time gap between when the downstream signal turns green after the upstream signal has turned green, so that gap is called as the offset, right? So with proper offset we can achieve the the coordination of these signals, right? So what would have happened if these were not coordinated? So if this offset was not proper, then the vehicle, for example this vehicle 1 v1, if the green happened later, so then it would have to come to a stop at the second signal, right? So that is not desirable, right? So this offset is important if you want to achieve the coordination. So these were the different parameters, and then we looked at an example of signal progression on one-way streets, right? So what happens in one-way streets? Again, one-way street is basically you have movement happening in only one direction, or the major movement is happening in only one direction. So you have a series of signals, with different distances, but close enough to each other, right? So therefore, these different signals are coordinated with each other, right? So the offsets are planned, right, such that the vehicle that is leaving from the signal A, that doesn't have to stop at any of the intermediate signals in that corridor, right? So that's what we looked at. So how to design that? So we looked at one numerical example, and then we were looking at different types of progression, right? So we have simple progression. The simple progression is basically is associated with what we have discussed now as the green wave, right? So see, a platoon which has got a green at one particular signal, that will keep getting green at all the downstream signals in throughout the corridor, right? So that is the simple progression, right? So it doesn't have to stop anywhere. Second is what is called as the flexible progression. So in simple progression, we will have only one. We will determine one set of timings, right? So that will give us the the green wave for the vehicles, right? So second, in the flexible progression, we'll change the settings, one or more times, in a day to achieve this progression, right? So in simple progression, we are not changing it. So we are finding that one interval that will give us, the signal coordination. Whereas in the flexible progression, we revise or change it, multiple times in a day, so that we'll keep getting this simple progression multiple times for the major flow. And then we have reverse progression. Right? So until now we have assumed that there is no Q that are present in the downstream signals, right? So but what happens if some vehicles are present say at signal B, and then a platoon is leaving from the signal A. So what happens in this case, if we are not considering this Q, right? So then we will get some particular offset, right? So T1, that is the time taken for this platoon to reach signal B. But because some vehicles are already in the queue, so the signal B must turn green much before than T1, so that the existing queue will get cleared up. So when the vehicle platoon reaches from A to B, so they can pass through without having to slow down, right? So therefore, so that's what we call as the reverse progression. When so when we have to when the signal downstream signal has to turn green before the upstream signal has turned green, so that's what we call as the reverse progression. And then we have alternating progression. So what happens in alternating progression? So in alternating progression, what happens, right? At any point in time, right? So if you look at what is the interval or type of interval that is there in throughout the corridor. Say if it is like red in A and green in B, again it will be red in C and then green in D, right? So as you can see, it is alternating with every consecutive intersection, right? So if this is what is happening, if this kind of setting is provided, we call that as the alternating progression. And then we have finally the uh, like there is one more, the second last one is double alternating progression. So where this same thing, but the alternating things will be happening in pairs, right? So we have A, B, C, D, E, F. So A and B will have red, C and D will have green, and then E and F will have red, and so on, right? So every pair of consecutive signals will have the same interval, same phase, right? So if that happens, we call that as the double alternating progression. And finally, we have the simultaneous progression. So what happens in simultaneous progression? So all of these signals will turn green at the same time, right? There is the offset is 0 for all of them, right? So they will all turn green at the same time. They will all be red at the same time. So when is this applicable? So this is applicable when the spacing is much smaller, right? So when these intersections are very closely located, so the vehicles will not take too much time to reach from one signal to the other, right? So in that case, it is desirable that we have 0 offset, right? So or the simultaneous progression, so that the signal coordination will be achieved, right? So those are the different types of signal progression coordination progressions that we have looked at. And then in the fourth lecture, we looked at how to design the signal progression for two-way streets, right? So two-way streets are designing progression for two-way streets is more difficult, right? So because when you are giving progression in one direction, so we have to remember that the other direction can face delays, right? So because this major direction is uninterrupted, so which means when this progression is happening, whatever demand is coming from the other side, so they will have to wait, right? So they cannot cross at the same time, right? So therefore there will be delays that will be happening. So to achieve progression on both directions simultaneously, so that is more difficult. So so we looked at one way to achieve this is by network closure, where we will be converting the movement into one-way traffic, right? So instead of two-way traffic, so we will be converting the signal progressions into one-way traffic, and therefore we will achieve the signal progression in two directions. And then we were looking at vehicle platoon dispersion. So what is this? So again, so platoon is basically a group of vehicles that are leaving from your up and upstream intersection towards your downstream intersection. So what happens is, so when you have larger gaps between the two intersections, so the vehicles, so initially once the upstream signal turns green, so they will be moving very closely, right? So this platoon will be more tightly packed, but as time progresses and the distance is more distance is covered between the two intersections, what happens, we will see that the gaps will become or will grow larger and larger, right? So the platoons will not be as tight as it was when it started. So this increasing gaps, right? So with time and space is what we call as the platoon dispersion, right? So and we have different factors that are affecting this. Like one is the interaction between these different vehicles, right? So some vehicles will try to overtake, some vehicle will try to change lane, and so on, right? And also different drivers, again, they will not always maintain the same speed, right? So when the distances are large, right? So again, the change in the speed across the different vehicles will be different. So therefore, the average speed will be changing. So the platoon will disperse, right? So so we looked at one particular model that quantifies how this dispersion will occur, right? So So this is important because when the platoon disperses too much, that will have problems with your signal coordination, right? So because you have to keep the green time for too long, right? If the dispersion is higher, to make all these vehicles pass through without interruption, right? Whereas if they were moving closely together, right? So then your green time that you have to provide will also be smaller. Right, so that's what we looked at in the final lecture for signal coordination, and then finally we are looking at oversaturated signals and the different mitigation strategies. So here we have different. So we know what is oversaturation. So oversaturation is when demand exceeds capacity, right? So that's what we call as oversaturation. Right, so when the facility is no longer able to satisfy all the incoming demand, but this can happen because of multiple reasons, right? So that's what we call as the different symptoms, right? So depending on what is causing this oversaturation, right? So our strategy will also vary. So first is we have overflow queue. So what happens in overflow queue? So overflow queue is basically, so you have too many vehicles. So this is your stop line. So you have too many vehicles that are there in the queue, and in one cycle, maybe only some portion of this queue is getting served, right? So the rest of them, so whoever was remaining in the queue and they are not served in a given cycle, so that is the overflow, right? So this happens when the demand is too large. All right, so second is approach spillback. So what happens in approach spillback? So basically, so this is happening with another signal. So we have one signal, so we have another signal, right? So so when the queue from the downstream signal, so when that starts affecting your upstream signal, right? So this is your downstream signal. So the queue formed from the downstream signal has grown so large, that it has reached your upstream signal, right? So because of this, so vehicles now cannot cross the upstream signal because of the queue from the downstream point, right? So this is what we are calling as the approach spillback. So what happens? So here the problem is not with the upstream signal, right? So they are not able to cross it because of the downstream signals problem. So our focus should be on, our strategy should be focused on relieving this queue at the downstream signal. Otherwise, whatever measure we take in the upstream part, so it is not going to help because the problem is from the downstream signal. So then we have the storage bay spillback. So what is storage bay spillback? So storage bay is basically, so in a signalized intersection, so you'll have through lanes, and also there will be lanes provided for turning vehicles, right? So at the signal, so whichever vehicles they have to say turn right, so they will when they are approaching this intersection, they will get into this storage bay, right? So and then wait for their phase to turn, and then they will turn. So through vehicles will be in the lane for the through vehicles. So what happens here? If the storage bay capacity is exceeded, let us say 4 vehicles can be accommodated in the storage bay. Let's say the 5th and the 6th vehicles that have approached also want to enter the storage bay. So what happens? So they will be blocking the approach to the through vehicle, right? So if this is a through vehicle, right? So even though the through lane is free, because the vehicles that are waiting to enter the storage bay are covering the approach, so this through vehicle cannot enter into the lane, and therefore they also have to wait. So this is what we call as the storage bay spillback. Second is the opposite of this, which is storage bay blocking. So here instead of the through vehicle getting affected, so here what we'll have is the number of vehicles in the through lane. So those are blocking the entry to the right storage bay, right? So if this all these vehicles are through vehicles in the start, right? So but they have blocked the access to the storage bay, right? And this right turning vehicle which is not able to access that storage bay yeah, because of the waiting through vehicles, right? So in this case, this is the storage bay blocking. And then we have starvation. So starvation is basically, so when you have unused capacity, right? So again, when you have the two signals, right? So suppose the downstream signal has turned green, but there are no vehicles present to be served, right? So but there is a red in the upstream signal, and then vehicles are waiting in the queue here, right? So there is a queue here, right? So but when the downstream signal turns green, so there is no demand available for it to serve, right? So this is starvation. The downstream signal is starved, right? So there is no demand that is being fed for this downstream signal to be served. So that is the another type of oversaturation. So finally we have the cross intersection blocking. So what happens in cross intersection blocking? So this is from different approaches. So when you have, this is at the same intersection. So when you have the queue from one approach, it has completely blocked the whole intersection. So because of this, the vehicles in the other approach, so when they get green, so they are not able to cross, right? So because the other phase has blocked the whole intersection, so because this, there is a problem in this direction, right? So the queue length has crossed the whole intersection, and therefore the other approach is not able to cross through. So this is the cross intersection blocking, right? So because it is from the other approach of the same intersection, right? So these are the different symptoms, and depending on what is causing this oversaturation, as you can see, our the strategy or the solution will also be varying, right? So and then we have the operational objectives for oversaturated conditions. So what is the objective here? Our objective is to maximize the throughput. Right. So what is the throughput? So the number of vehicles that we are able to serve, right, in a given period of time. So that we want to maximize that, right? So or the other way of saying this, we want to minimize the delay or the queue, right? So we do not want too much vehicle or user delay, or we don't want the queue to grow large, right? So this is the objective that we want to achieve, right? So when we are dealing with this oversaturated conditions. So for these, we looked at different mitigation strategies, like different 13 different 16 different types of mitigation strategies, right? So depending on what the problem is, right? So that's what we covered in week 8. Now let's move into some of the problems related to these. So the first question is, for an actuated signal, the presence detection with a 95-foot detection length is used on an intersection approach. The front edge of the detector rests on the stop line. Assume a head-to-head spacing between the vehicles in the queue equal to 20 feet. The startup last time is 3 seconds. Saturation at bay is 2 seconds. Estimate the value of G min high in seconds. Okay, so here we want to. So here we are looking at an actuated signal, right? So which has a area detection, right? So that is what we call as a presence detection. Okay, and the length of this the detection area is 95 feet from the stop line of the intersection. Okay, so there is no gap between the stop line and this this detection area. And so we are assuming a space headway of 20 feet. The startup last time and saturation headway are given to us. We want to find the minimum green time, right? So again, for the minimum green time for the saturated phase, for the presence detection, so we can have two values. We have a range of G min, so G min low and G min high. So depending on how many vehicles, what is the assumption that we are making about the number of vehicles. Okay, so here we want to find out the upper end of this Gmin. Okay, so how do we do this? So the answer is 13 seconds. So to find the Gmin, okay. So once the signal turns green, right? So there is the startup last time, right? So which is not being utilized, right? So that must be provided, right? So this Gmin should contain the startup last time. So because it will always be present, so we have to take into account of the startup last time. So once the startup last time is removed, right, is taken care of, then we have to provide the green time for clearing the vehicles that are in that particular approach, right? So how do we know how much time to provide? So that's where the saturation headway will come into picture, right? So what is the saturation headway? It is nothing but the time gap between consecutive vehicles to cross the stop line, right? So if the saturation headway is h and the number of vehicles in the intersection is small n, then the total time to clear n vehicles will be n times h, right? So this is fine because we have taken into account the startup last time, right? So because the saturation headway is not constant for all the vehicles, right? For the first 4 vehicles, so it will be higher than the saturation headway, but it is taken care of in the startup last time. So we can assume that all the n vehicles that are waiting can pass through at the saturation headway, right? So here I say there is low and high, right? So the low is basically, so when you assume that there is only one vehicle that is present in the approach. So when n is equal to 1, so whatever Gmin that you get, that is the Gmin low. So Gmin high will be n is equal to the detector length by the space headway. Right, so you take the floor of this ratio between the detector length and the space headway. So that is the maximum number of vehicles that can be present in the the detector area, right? So that the green corresponding to that is called the Gmin height. Okay, here we want to find out this Gmin height. So first we want to find out what is the value of n, right? So what is the value of n? So for that, the detector length is given as 95 feet. Okay, so divided by the space headway, I think was given as 20 feet. Right? Yeah, so it is 90 feet and the spacing is given as 20 feet. So last time that is L1, so that is 3 seconds. Saturation headway H is 2 seconds. So Gmin height is equal to L1 plus H into N. So L1 is 3 seconds plus 2 times of 95 feet by 20 feet. So 3 is so 9.5. We have to take the floor of this, right? So see 9.5. We can't have 9.5 vehicles, right? So we always round it up. Okay, so we'll take it as 10. So 20 should be 23. It's not 13. Should be 23. Okay, so I think I made a mistake here. So here you cannot cancel. You cannot cancel this too, because this 95 by 20 is within a function, right? So it is within your floor function. So you have to multiply the two only after you take the only after you simplify this part, right? So it is 3 plus 2 times, this will become 95 by 20, right? So it is rounded up, so it will become 5. So then it is 3 plus 7. So 30. So in that case, this is correct, right? So I made a mistake when doing the simplification. So it should be, first we have to find the number of vehicles, then multiply it with the headwind. So 13 seconds is the minimum that we have to provide, right? So we have to is the minimum that is required for this particular approach, right? It can be more than that if more vehicles are present in that approach, right? So there could be vehicles that are beyond the detector as well. So but this is the absolute minimum, so we cannot provide less than 13 seconds. So the second question is, there are 3 signals A, B and C that are closely spaced from each other, with the distance between 2 consecutive signals being 200 meters on an urban arterial as shown in the figure. So the figure is here. So we have 3 signals A, B and C. So the gap between the consecutive pairs is 200 meters. So it is desired to establish the offsets between these signals for signal coordination, considering the primary flow only in one direction by having 2 lanes and a bandwidth efficiency of 36%. The desired progression speed is 45 km per hour. The saturation headway may be taken as 2 seconds per vehicle and the startup last time is 2.5 seconds. The first question is, what is the ideal offset in seconds between the signals A and C, assuming that vehicles arriving at the upstream intersection are already in a progression? So that is, they are moving as a platoon at the initiation of the green. The second question is, what is the adjusted offset in seconds between signal A and signal B, assuming that an average queue of 2 vehicles per lane is expected at the downstream intersection at the initiation of the green? Assume that the vehicles again at upstream signal are already in a progression at the initiation of green. And finally, we have to find the bandwidth capacity in the primary direction. Okay, let's start with one by one. First, we'll do part A. So in part A, we are talking about ideal offset between the signals A and C. Okay, so what is an ideal offset? So ideal offset is basically, so you assume that the vehicles are traveling at a progression speed, okay, from the upstream signal, and there is no queue. At the downstream signal, right? So whenever they are reaching the downstream signal, there is no queue that is present there. So in this case, whatever is the offset that needs to be provided, so that is called as the ideal offset. So the value is 32 seconds. So how do we get that? So T ideal. So T ideal is basically what is the time that is taken for these vehicles to cross the L distance that is there between the 2 signals. Okay. Progression. Okay. So here, so this is nothing but distance between the signals. So the travel speed. Okay. So here, what do we have? So here we are given that the distance is, so here we are talking about the signals A and C, right? So the total distance is, so A into C. So L is 200 meters plus another 200 meters. So first 200 is for distance between A and B. Second 200 is between B and C. So the total distance is 400 meters. And the progression speed, so progression speed, it is given as 45 kilometers per hour, right? So you want to multiply it by 5 by 18, so to get it in meters per second, right? So why? Because finally we want the T ideal in seconds, right? So the numerator is in meters, right? So we are converting the speed into meters per second. So that will be 400 divided by, this will be 12.5 meter per second. So that will give you 32 seconds. Okay. So what does this mean? So when signal A turns green, so 32 seconds later, signal C has to turn green, right? So this is the ideal offset between the signals A and C, assuming that there is no queue that is present in between. Okay, so that is the first part. Second part is what is the adjusted offset between signals A and B, assuming that an average queue of 2 vehicles per lane is expected at the downstream intersection, which is signal B, at the initiation of green. Okay, so here, so this is for part A. So for part B, so let us assume if it is ideal. So what do we do? If it is ideal, so it will be L by the V progression. But here the L will change. It will be the distance between the signals A and B. So this is in the ideal case, but it is not enough, right? So we have A, we have B, and so some vehicles are, waiting, right? So if the time taken to reach from A to B, right? So that is T ideal. So the signal B has to turn green before T ideal, so that the vehicles that are there in the queue are cleared, right? So when the platoon arrives at B, right? So therefore we know that it has to be smaller than this value. So we have to subtract something. So what is that something that we have to subtract? So that something is nothing but the time it takes to clear the vehicles that are there in the signal B. So how much time it will take to clear the vehicles in signal B? That is what we saw in the previous problem, right? So depending on the number of vehicles, so one is we have to take into account the startup last time, because these vehicles are stopped, right? So because when the signal turns green at P, so some time will be lost. So that is L1, your startup last time, plus the saturation headway into the number of vehicles in Q. So this will be your adjusted offset. Okay, but here what do we know? We know the distance, we know the progression speed, right? So startup last time is given, saturation headway is also given, so the number of vehicles in the queue, so that one we need. So that also is given as 2 vehicles per lane, right? And how many lanes are there? It is given that there are 2 lanes. So consider primary flow in one direction having 2 lanes, right? So 2 vehicles per lane, and there are 2 lanes, which means there are 4 vehicles in the queue. So the adjusted offset would be 200 meters by 12.5 meters per second minus the startup last time is 3 seconds plus the saturation headway is 2 seconds and the number of vehicles in the queue is 4. Okay, startup last time is 2.5 in this problem. It was 3 in the previous problem. So 2.5 plus minus, which is coming out as 21.5. This is just 21.5 seconds. So this I calculated assuming that there was only one lane. Okay, so in that case, it is that. So but now assuming that there are 2 lanes, so it will be 21.5 seconds. So instead of 32 seconds, uh, this is again I made a mistake. It is not 32. That was for 400 meters of travel. It's for 200 meters. The ideal offset is 16 seconds, right? So it is 16 minus 2.5 minus 8. So that will be 5.5. Okay. So that is the adjusted offset between the signals A and B. Okay. So I confused between A, C. So in the second problem it is A and B, right? So the ideal offset is 16, but because there are 4 vehicles that are there in the queue, it's because 2 lanes and 2 vehicles per lane. So there are 4 vehicles in the queue. The saturation headway is 2 seconds per vehicle. So 8 seconds is needed for clearing them, plus another 2.5 seconds for the startup loss time. So it has to start 5.5 seconds after signal A turns green, so that there will be progression happen. And then the third question was to find the bandwidth, right? So corresponding to a bandwidth efficiency of 36%. Okay, so how do we find the bandwidth capacity? So it is your saturation flow, which is that 3600 by h, into the number of lanes multiplied by your bandwidth efficiency in percentage. Okay, so it is 3600 by saturation headway, 2 seconds, into the number of lanes is 2, multiplied by your bandwidth efficiency, which is 0.36, right? So 36%. So this will give you 1296 vehicles per hour. Okay. So moving on to question number 3. So here we want to match the different mitigation strategies given in column X with the corresponding definition or the description given in column Y. Okay, so we have 4 mitigation strategies given. So one is negative offset, 2 is phase reservice, 3 is phase truncation, and 4 is gating. The different descriptions given are termination of a green interval, impedes traffic at appropriate upstream points, oversaturated phase is served twice, and allows for downstream queue to dissipate. So here are some matchings given. Okay, so this we looked at in the last lecture, right? So what are the different oversaturation symptoms and the mitigation strategies? Okay, so here the first one, negative offset. So negative offset means the offset between the signal pairs, that is a negative value. So as we saw earlier, so it is the difference between the time a downstream signal turns green minus the time an upstream signal turns green, right? So after an upstream signal turned green at time t1, so downstream signal turns green at time t2, right? So this is usually a positive quantity, right? But in negative offset, what happens is this will be negative, this value. So what does this mean? It means that before the upstream signal turns green, the downstream signal turns green, right? So why do we do this? Because to when there is a large queue that is waiting in the downstream signal, so we to clear this before the plateau arrives from the upstream signal, so we give a negative offset, right? So which means that it has to be matched with D here. Okay, so to allow for downstream queue to dissipate. The second is phase reservice. So phase reservice means, so when there is a huge demand for a particular particular phase of movement, so in that case we may give the phase 2 times, right? So that oversaturated phase may be given green more than 1 time, right? So that is called as the phase reservice, because this particular phase is the oversaturated one. So therefore that has to be cleared so that the queues do not grow long. So that is what is called as the phase reservice, where the oversaturated phase is served twice. And third is phase truncation. So this is the opposite of this, right? So here we truncate the phase. So even though there is some demand, so this is not the oversaturated condition, but to give the green to the other phase, which is oversaturated or the major movement. So we can terminate the green interval, for a particular phase with the lesser traffic, right? So that is the phase truncation. And finally, we have gating. So gating, or it is also called as metering. So here, what do? We filter the traffic. We, restrict the traffic that is incoming into a particular intersection. So that particular intersection does not become oversaturated. By limiting the demand. So because the demand, when it is much higher than the capacity, so that's when we have the queues growing, right? So instead of that happening, we limit the demand that is coming into the intersection by metering or gating them, right? So we are stopping them at upstream points, at multiple upstream points, so that the traffic that is entering the signal intersection will be smaller. So that is the gating final one. So the correct matches: 1 is matched with B, 2 is matched with C, 3 is matched with A, and 4 is matched with B. And that is given in option B. So B is the right. Then question number 4 is, which of the following statements regarding offsets in signal coordination are incorrect? So options are: offsets refer to the difference between the two red initiation times of upstream and downstream signals. Option B is, the higher the travel speed, the smaller will be the required offset between upstream and downstream signals. C is, for stopped vehicles at the upstream signal, startup last time must be added to the ideal offset. And for D, in case of a queue at the downstream signal, offsets must be adjusted before the arrival of a platoon from the upstream signal. Okay, so here we are talking about the signal offsets, and we want to identify the incorrect statements, right? So first one, the offsets refer to the difference between the two red initiation times of upstream and downstream signals. So this is an incorrect statement. Why? Because offset is the difference between the time it takes, between the green initiations, right? It's not the time difference between the red initiation, the time difference between the green initiation of the upstream and the downstream signals, right? So therefore A is incorrect. B is, the higher the travel speed, the smaller will be the required offset between the upstream and the downstream signals. So this is correct, right? So this, as we saw in your offset, so this is depending on, directly it is proportional to the length, and it is inversely proportional to the velocity or the speed, right? So if your speed goes up, right, so for the same distance, here offset will come down, right? So therefore, the higher the travel speed, the offset required will be smaller. So B is correct. C is, for stopped vehicles at the upstream signal, startup last time must be added to the ideal offset. So this is also correct, right? So when we calculated ideal offset, right, so we used only L plus V. So we did not add the startup last time here, because in that problem we had assumed that the vehicles were already moving when the signal had turned green, right? So they were not in the stop condition. The startup last time is applicable only when the vehicles are stopped, and then once the green signal turns green, so they have to accelerate. So in that condition, we have to assume the startup last time, right? So but when they are already in motion, so we do not have to consider. That's why in the problem we did not consider it. But when the vehicles are stopped, as given in this condition, so we have to add the ideal, the startup last time as well to the ideal offset. So C is correct. And D is, in case of a queue at the downstream signal, offsets must be adjusted before the arrival of a platoon from the upstream signal. So this is also correct. This is exactly what we did in the previous problem, right? So there was some queue that were present at the signal B. So we calculate the adjusted offset. So the ideal offset was adjusted by removing the startup loss time for the downstream signal and the time taken to clear the queue that is present, right? So this is the adjustment that we are doing to the ideal offset. Okay, so therefore D is also correct. So these three are correct statements. Only A is the incorrect statement. Okay, question number 5 is for a two-phase semi-actuated signal. So this is the signal setting. So we have two phases A and B. For phase A, we have actuation, and for phase B, there is no actuation. Okay, and the green splits are given as 12 seconds and 28 seconds for the two phases. Change interval is 3 and 4 seconds, and the altered interval or the clearance interval is 1 second and 2 seconds. So we want to find out what is the minimum green time for the actuated phase. So the minimum green time is for the actuated phase is 8 seconds. So this is also data that is given. To account for the peak cycle by cycle demand, a multiplying factor of 1.5 is chosen. So what we want to find is the value of the critical cycle length. Okay, so for critical cycle length, what we have to do is we have to assume maximum. We have to find out what is the maximum green time for the actuated phase, right? So for phase A, and then we have to take the minimum green time for the non-actuated phase, and then add the change intervals and the altered intervals. And this is all done for the peak peak demand condition. Okay, not for the condition that is given in the table, but we have to consider the peak condition, and that will give you the critical cycle length. Okay, so here how do you get the maximum times for A and B? So so it is given that the green split is 12 seconds, right? So for GA it is 12 seconds. So we will multiply it by 1.5. Why? Because the multiplication factor is 1.5 for the peak conditions, right? So we can multiply the given green split by 1.5 to get the value for the or the maximum value that we want. So this will be 18 seconds. Now we have to check. So this is our estimate, right? So we have to check whether this is sufficient or not. So that we have to compare that with the minimum green time. The minimum green time is 8 seconds. So this is greater than Gmin for A. So this value is okay, right? So we are providing more than the minimum green time. So this calculation is fine. Next, for the phase B, also we have to take consider the peak condition. So 28 into 1.5, so that will be 42 seconds. Okay, so there is no minimum time that is given for this, so this is fine. And for the yellow and altered intervals, so we can take the values as such. We don't have to multiply it by 1.5. So the critical cycle length will be 18 seconds plus 42 seconds for the two phases, plus what is the change interval is 3 and 4 seconds, and the altered intervals are 1 and 2 seconds for the two phases, right? So if you sum them all up, so you will get 70 seconds as the critical cycle length, right? So this is for the peak condition, right? So that's the final answer. So we have 4 options. So option C is the right one, which is 70 seconds. Okay, so the next problem is to accept or reject the given statement. So the advanced coordination system requires the practitioner to define a consistent cycle length for the corridor as well as splits and offsets for each timing plan. Right, so here, so we talked about 2 different types, right? So of the signal coordination, one is traditional, another is advanced. So what is given here? So this whole definition. So this is applicable for the traditional signal coordination type, right? So in that, the practitioner must define the consistent cycle length as well as the split and the offsets, right? So but whereas in the advanced, there is no explicit specification. Right, so adjustments come from the measurements. From the detectors, what are measurements we take? So those are used directly to change the cycle lengths in the plants, right? So in the advanced one, we do not have to define the cycle length and the splits and the offsets. So therefore, we reject the given statement because it is incorrect, right? So it is not applicable for the advanced coordination system. Next, question number 7 is again an accept or reject. Shorter travel time between signals result in greater vehicle plateau dispersion. So again, so we discussed about this in the vehicle plateau dispersion, right? So here, so when the distances are large, right? So when the distances are large, so dispersion will be so if d increases, dispersion will also increase, right? So if d is higher, so travel time will also be high. Okay, so larger distances will lead to larger travel times, which will also lead to larger dispersions, right? So on the other hand, so the reverse is also true. So shorter travel time, right? So which means that the dispersion will be smaller, given that all the other factors are the same. So the travel times are short, which means that the signal in the intersections are close by. In that case, dispersion will be smaller. It will not be higher. So, but here it is given that it will be higher. So therefore, we reject this statement as well. Here, next question, we have to match the vehicle progression with the corresponding description. So we discussed the different types of progression, so which are the double alternating progression, simple progression, reverse progression, simultaneous progression. And we have 4 descriptions. A is downstream signal oscillates between green, green, red, red, green, green, red, red, and so on. B is used for very closely spaced signals or for rather high vehicle speeds. C is ideal offset is negative. And D is green wave advances with the vehicle. So the different matchings are given here. So the right one is, so double alternating progression. So as we already discussed, so this is what is described in option A, right? So when you have a series of signals, every pair of signals, they will be having the same interval, and then it changes for alternating pairs. So A and B, if they have red, C and D will be having green, E and F will be having red, and so on, right? So this kind of pattern is there, so we call it as the double alternating progression. So that is given in option A, or in column Y, description A, where the downstream signals alternates between green, green, red, red, green, green, red, red, and so on, right? So this is the double alternating progression. Next we have simple progression. Simple progression, as I said, it is nothing but the vehicles passing through the signal, the downstream signals without having to wait. So that we call as the green wave, right? So when they are leaving from A, they have a green, and by the time they reach B, they will get another green, and then by the time they reach C, they will get green, and so on. So that is what we call as the green wave, series of greens. So that advances with the vehicle, right? So as the vehicles are reaching the different signals, so the signals are turning green. So that is in the simple progression. And 3 is reverse progression. So what is reverse progression? So reverse progression is given in option C, that the ideal offset is negative. So as I said, when the T2 minus T1, so that is the time gap between the initiation of green and the downstream signal minus the initiation of green and the upstream signal. If that is less than 0, right? So that is the negative offset. So this when we give, so when the reverse progression is needed, so what happens is the Q is present in the downstream signal, right? So therefore the offset has to be negative so that the Q is cleared before the plateau arrives from the upstream signal. So that is the reverse progression. And 4th is simultaneous progression, where the offset is 0, right? So all the signals will be turning green at the same time, right? So that is called as the simultaneous progression, and that this is applicable when the signals are closely spaced, right? So which means that the travel time between the signals are smaller, or even if the distances are there but the vehicles are traveling at a high speed, then also the travel time will become smaller, right? So they are all turning green at the same time, so that the vehicles can easily pass through. So that is given in description B. So the right matching is 1 is matched with A, 2 is matched with B, 3 is matched with C, and 4 is matched with B. So that is given in option D. So the right option is option D. Question 9 is, which of the following statements regarding the actuated signals are true? The options are, the actuated phase will terminate if the Gmax for that phase is achieved. Actuated signals have variable phase sequences, but cycle length remains fixed. For semi-actuated operation, actuated phases are used to serve the minor movements, and passage time should be designed such that staggering vehicles may not retain the green. Okay. So here we want to identify the correct statement. So first one is, the actuated phase will terminate if the Gmax for that phase is achieved. So this is true, right? As I said, we have Gmin as well as Gmax, right? So the green time that is provided for a phase should be between these two values, right? It can't be shorter than Gmin. It cannot be longer than Gmax as well, right? So therefore, so if it is less than Gmin, right? So whatever is the, depending on demand, even if the G required is less than Gmin, you will still give Gmin, right? So it will not be terminated. But even if there is a demand available and Gmax is attained, we will not extend the green time, right? So we will go for the next phase, right? So therefore, it will be terminated if Gmax is achieved. So A is correct. So B is, actuated signals have variable phase sequences, but cycle lengths remain fixed. So this is incorrect, right? So in actuated signal, not just phase sequences, cycle lengths can also vary. The interval lengths can also vary, right? So cycle lengths need not be fixed, right? So that is only in the pre-time signal. So B is incorrect. C is, for semi-actuated operation, the actuated phases are used to serve the minor movement. So this is correct. So again, from our earlier discussion, so when we have fully actuated signal, so all approaches are, all phases are actuated. But in semi-actuated, the minor phase is only actuated. So other phase is not an actuated phase, right? So that is the priority movement. So that will be getting the green, and whenever there is movement on the minor phase, right? So which will be smaller. So then only we will, the phase will change for the the other phase. So that is in the semi-actuated one. So that is more suitable when we have a major road moving passing through a minor road, and the minor road will be the actuated one. So that is correct. And D is, passage time should be designed such that straggling vehicles may not retain the green. So this is also correct. So what is passage time? So passage time is basically, so when you have is basically the time of time when that particular phase is idle, right? So when you have green time, but no vehicle is served. Right, so the portion of the green time where the vehicles are not being served, so that will be the passage time, right? So in this passage time, right, so if it is if no vehicle is coming for a long period of time, so that is this passage time. When it crosses this passage time threshold, then we will go to the next phase, right? So given that we are above the Gmin, right? So if passage time is exceeded and Gmin is exceeded, phase change occurs, right? So if we have satisfied our Gmin condition and we have also exceeded the passage time, which means that there is no demand to be served, right? So in that case, there is no need to keep giving the green for this phase. You will change it. But if the Gmin is exceeded but passage time is not exceeded, which means that some vehicle is coming, after the last vehicle had crossed, some time has elapsed, but another vehicle has come before the passage time has elapsed. So in that case, we will retain the the same phase, right? So what happens here if our passage time is too long? So what happens is even longer headways will lead to retaining the the green, right? So and eventually what will happen is in every cycle we will be going towards the G max for that phase, right? So this happens if the passage time is too long, right? So that's what is given here. If the passage time is too long, the straggling vehicles will retain the green, so that our design should be such that the straggling vehicles do not retain the green. So straggling vehicles means, so these are not part of your uh, the platoon, right? So these are arriving randomly, right? So we do not want to keep the green for too long to serve all these randomly arriving vehicles, right? So we want to increase our throughput, right? So we don't want to keep keep the green just for one vehicle that is coming after a long time, right? So that time the other phase will be getting a large delay. So therefore our passage time should be properly designed so that this situation does not occur, right? So it should not be too small, it should not be too long as well. So the right options are A, C and D. Then question number 10, the two-way total peak hour traffic volume between two intersections which are 920 meters apart is 4250 vehicles per hour. So which of the following statements is incorrect with respect to the variant model of the coupling index? The option is the value of CA is equal to 13, therefore signal coordination between the intersections can be considered. Option B is value of CA is 13, therefore signal coordination between the intersection is desirable. C is the value of CA is 0.88, therefore signal coordination between the intersection is not required. And D is the value of CA is 1.41, therefore signal coordination between the intersection is desirable. So here how do we do this? So this is from the second lecture where we looked at how to assess whether a signal coordination is needed or not, right? So one was the grouping, right? So depending on the distance between the intersections. So the other one was to use the different indices, right? So we have multiple indices that we have looked at. So one of that is the variant of the coupling index, right? So coupling index is basically V by D, okay? So V is your volume of the approach and D is the distance between intersections, right? So variant is V by D square, okay? So that is the CA variant, and depending on the value of the CA, so we have different conditions. So the right option is A, but first we have to determine whether the CA value is correct. Okay, so the CA for the variant model is V by D square. So where V is volume in thousands of vehicles per hour. Okay, it's not in vehicles per hour, it is thousands of vehicles per hour. And D is distance in miles. Okay, so we have to take be careful of the units that we are using here. So in the problem it is given as D is 920 meters. So we have to convert this into miles. If we convert it, it will be around 0.57 miles. And the approach volume, what it is given as 4,250 vehicles per hour. Right? Or if you have to convert this into thousands of vehicles, it will be 4.25 thousand vehicles per hour. Okay, that is the unit that we are using in the variant model. Okay, so this should be 4.25 by 0.57 square, and that would come out to be 13. Okay, So therefore, the CI value is 13. So it is between options A or B, right? So C and D is obviously incorrect, right? So because it is saying 0.18 and 1.41, so it is either A or B. So here we need to remember the the table. Okay, so what is the value of CI variant, right? And then what is the criteria? So if it is less than 1, if the value of CI is less than 1, then no coordination is needed between the signals. Right, so this is one condition. And if it is greater than 50, then coordination is desirable. But if it is between 1 and 50, then coordination can be considered. This is the condition that we will be applying. Okay, so here because our CI value is 13, that is between 1 and 50, so we can consider coordination, right? It's not necessary to provide the coordination, but if we provide it, it may be useful, right? So but if it is exceeding 50, then there is a strong case for going for signal coordination, and if it is less than 1, so you don't have to consider, right? So it's not going to help much if you have less than 1. But since here is between 1 and 50, so we can consider if it is if the delays can be significantly minimized, so we can go for the signal coordination in this case. That will be beneficial. So question number 11 is accept or reject. So the passage detection can discern the number of vehicles stored in the detection area. So here this is from the features of the controller. So detection type. So we have passage and then presence. Right. So passage is point detection. Presence is area detection. Right. So here we cannot determine the number of vehicles. Right. So in passage detection. So passage detection means the number of when a vehicle crosses your detection point. Right. So when your vehicle crosses the detection point, so a pulse will be generated. Right. So even if multiple vehicles are crossing, so you will not be counting the number of pulses that are being generated, right? So even a single vehicle, so even it will have a site area, right? So it can generate multiple pulses, right? So but you will not count the number of pulses. You will only count whether a pulse came or not, right? So whether at least one vehicle is present or not. So that's all we do in the passage detection. So the number of vehicles is not stored, right? So therefore, so therefore, in our detection area, we do not know how many vehicles are available. So therefore, this given statement is incorrect. So this answer is wrong. It should be rejected, right? So because this passage detection, so our detection area is a single point, right? So we cannot determine the number of vehicles that are there in this condition. The right answer is B, not A. Question 12 is which of the following statements are correct with respect to the minimum green time in case of the actuated signals? The options are Gmin is based on the type and location of detectors. Right, so this is true. Why? Because in the case of passive detectors, the Gmin will be startup loss time plus the time taken for so we assume that all the vehicles between the passage point and the stop line, so the area between this passage point and the stop line is covered by vehicles, right? So if the length of the gap between the stop line and the detector is d, so and we assume some space headway sh, okay. So this into your saturation headway. So this is for the passage type. For the presence type, be L1 plus N, right? So this N comes from the detection area, right? So therefore, it will change. The G-min will change based on the type and the location of the detectors, right? So the D also affects, and also the type of the detector also affects the G-min calculation. So therefore, A is the correct statement. B is for point detector located D free from the stop line, assumes that a queue of vehicles fully occupies the distance D. So this is also correct. So based on that only we have this particular formula here, right? So we assume that all the length is occupied by the vehicles, right? Because we are not keeping track of how many vehicles are there. So we assume that the whole length is covered with vehicles. And C is for point detector, the minimum green time can vary. No, it does not vary. Why? Because every time we will assume that all the vehicles, like the throughout the length is assumed to be covered with vehicles, right? So because whenever we have detected a presence, so regardless of how many times the pulses come, we always assume that the whole length D is filled with vehicles. Therefore, our calculation does not vary, right? So the saturation that we start up last time is not going to change. It's here D is also fixed, right? So the space headway also you assume to be the same, right? So therefore the G-min will not vary for the point detection case. And for the presence detectors, the minimum green time is fixed. So this is incorrect because here the L1 and H are fixed, but N can vary, right? So therefore the number of, because in presence detectors we can determine the number of vehicles that are present. Therefore the G-min for the presence detector can vary. It's not fixed. It need not be fixed. Okay. So the right options are only option A and option B. Okay, next question number 30. Accept or reject. The critical cycle for a fully actuated signal is the one in which each phase reaches its maximum green time. Okay, so this is the correct statement. Right, so here we are talking about a critical cycle. So critical cycle means where we have the peak demand, right? So which means that there is enough demand, right, to be satisfied, so that every phase, whatever is the maximum limit of the green, so that is achieved. So there is enough demand for a phase to go up to its maximum green. So that phase is the critical one. Okay, so because there is a higher demand, right? It's more intense demand. So in that case, all the phases are enough demand is there. So all of them is reaching their maximum value. So therefore, that is what we call as the critical cycle. So that particular definition is correct. Then question number 14 is which of the following statement is correct with respect to bandwidth and signal coordination? So option A, bandwidth indicates the time gap between the start of green in the current cycle and start of green in the next cycle at the approach of an intersection. This is incorrect. Right, so this is nothing but the cycle. So this is not the definition of bandwidth. This is the definition of the cycle length, right? So time gap between the same signal indication, not the same at a given approach. So that is cycle length, not bandwidth. The bandwidth is nothing but the time gap between the first and the last pair of vehicle trajectories, so which went through without having to stop or slow down, right? So which were part of the the progression. So A is incorrect. B is bandwidth can be different for each direction of travel. This is true, right? So for say northbound and southbound, the bandwidth need not be the same, right? So they can be different. So C is as the bandwidth gets narrower, the potential progression opportunities increases for the vehicles. So this is incorrect because when you have larger bandwidth, which means that more vehicles can pass through, right? So which means there is large opportunities for the vehicles to travel in a platoon, right? So number of vehicles can be more, that can be served will be more. Okay, so but here it says the opposite. When the bandwidth is smaller, the progression opportunities are higher. So that is not true. And say B, since B is correct, so none of these is not applicable as well. So the right option is only option B. Then question number 50 is which of the following statements are correct with respect to vehicle platoon dispersion and signal coordination? Option A is random arrival of vehicles provide the maximum benefit in coordinated system operation. So this is incorrect, right? As we saw earlier, so when the platoon dispersion happens, right? So so that is not beneficial. So when the vehicles are traveling as a group, right? So then it is easier, right? So you don't have to provide a large cycle length to cater to all of them. But if they are arriving randomly, you have to keep the cycle length, the green times larger for all of them to travel, right? So this is like that. This will lead to that straggling, operation that we looked at earlier with respect to the passage time. So that is not desirable, and right, it's not very efficient as well. So B is as vehicle platoon moves over time and distance from upstream intersection, it initially tends to disperse while it reaches in a tight form as it arrives at the downstream intersection. So this is also not true. So when dispersion happens, it will only keep on increasing, right? So it will not suddenly become smaller, right? So here it says that it will start like this, right? But it will become something like this, and then when it reaches the other signal, again it will become like this, right? This is upstream signal, this is the downstream signal, right? So this is what the statement is saying, right? It is starting as a platoon, disperses, and then again becomes tighter platoon when it reaches the downstream. That doesn't happen. So it start like this and it will be like this only. It won't come back into this tighter form at the downstream signal. So provided that it's not stopping here, right? So provided the coordination is there and they are able to pass through, so they are able to slow down, right? So in that case, it will still be arriving in this form only. C is with longer travel time, drivers tend to deviate from the average travel time. So this is true. So this is what leads to higher dispersion with more time, right? So when there is a longer time, so again different drivers will be traveling from different speeds. So the average speed will change. That is leading to the dispersion in the platoon. And these vehicle platoons with large number of vehicles disperse less. This is also true. As the platoon size increases, there is less opportunities for drivers, to overtake or change the lanes, right? So they will be trying to travel, at the same speed, right? So, but what happens is, even though the dispersion will be less, your average speed can come down, and there is large group. Average speed will go down, right? But the dispersion will be lesser. So therefore, the right options are options C and D. Okay. So with that, we are coming to the end of week 8. Okay. So as usual, if you have any questions or queries, so you can raise that in the discussion forum and then it will be answered. Okay. So with that, we will close today's session and we will continue with our discussions from next week. Okay. Thank you and see you in next week, week number 9.